So who Dectris is? As I learned on the lunch break, many of you actually already worked with Dectris detectors. But for some of you who did not, Dectris is a Swiss company. We are originally spin-off of PSI, and as would be expected of the spin-off of PSI, we closely work with science. And our mission is to enable scientific discoveries and advance human health by pushing the limits of detecting technology. And we also strive to provide the most reliable and high-performance X-ray and electron detectors. Once we only started in 2006, we worked mostly with synchrotron, but later on through our journey, we also went into laboratory market, and recently we also entered electron microscopy market. And right now we are world leading manufacturer of the X-ray and electron detectors. Our technology is basically based on the hybrid pixel readout. In this case, hybrid means that the layer where the detection of particles happens is separated from the readout layer, the CMOS ASIC. Those two are separated with conducting indium bump. And by doing this separation, we can optimize the capacitance of each layer so that the sensor layer has the high detection efficiency, while the readout chip has the lowest possible noise signal. And each pixel acts like a small, tiny, individual independent detector. By reading out the information from all pixels of one detector, we can obtain the images shown here. So that's the image acquired at ESRF with our collaborator, Michiel Hanfland. This detector has 9 million pixels, which basically means 9 million independent small detectors. You can see here a diffraction pattern acquired with 30 kV X-rays and lanthanum hexabarite sample. So our flagship detector, EIGER2, has 16 million, the biggest of the EIGER2s has 16 million pixels and can count at 550 Hertz. This would produce 20 gigabytes of uncompressed data per second. EIGER2 detectors 2 stands here for the 2 energy discriminating thresholds, and thus having 2 energy discriminating thresholds, we double the amount of data that we read out from the detector. To handle this data output in an efficient way, we organized our data acquisition pipeline in the following way. So we've got the detector head that registers the signals and then passes the data to the detector control unit. This is the server that has performance that would match the performance of the detector head. On the DCU, we have data interfaces that handle the data and output data in the specific format. So we have a monitor interface. That one is rather slow. It handles data with frame rates below 10 Hertz and outputs data at TIFF format. Then we've got stream and stream 2. Those two output data as the ZROM-Q messages compressed and encoded way. And then we've got Filewriter and Filewriter 2, and those two save the data on the detector control unit in the HDF5 format. Why would we go for the HDF5 format? Well, I actually also heard during the lunch break that some of you worked with our earlier generation detectors, with Pilatus detectors, and those were handling data in CBF format. But some years ago, we started development of a new generation of detectors, EIGER1 back then, and we already realized that those detectors produce the data with the higher frame rate, and CBF cannot handle these higher frame rates. That's why, of course, there was a need to find another data format that would be container-like data format that can handle fast and efficient compression. And of course, the requirements for this data format would be that this data format should be easily readable, universal, that we can, that different customers at different facilities would acquire data in the same way, and that would have a fast compression. So that's why we choose the HDF, and we also applied the Nexus standard for the semantics of how the data is organized. The Nexus standard is not a competition for the HDF, but just a rule how to structure the data inside of the HDF file. So Nexus defines in which way should we write the data, which type of the data, how to organize the hierarchy of the data, and so on. By having this standard, we can guarantee that every customer that takes the data would have the same exactly structure of the data they produce. And if we go inside of how this file is structured on the programming level, each of the groups is in fact a Nexus class. So how does the real data file looks like, the HDF data file? This is a screenshot taken with HDF viewer. You can see on the left is like human readable names of the groups of the data that is inside of the file. And on the right is the Nexus semantics. Basically, it specifies what Nexus class is that, what data type, and the size, and so on, so the developer can quickly decide on how to handle this data. Then, of course, the data that acquired with our detectors is a physics data, and then it's important to know how to handle information about detector position, the sample, and the source. And for this, Dectris was for a long time a part of the community NXmx Gold standard, the gold standard for macromolecular crystallography that basically defines the procedure of how to save this physics data inside of the HDF5 metadata. I've seen that last year this talk was presented by Herbert Bernstein on the gold standard for macromolecular crystallography. So if you would like to know more in details how it works, the NXmx standard, I would refer to this talk or to the paper that we also wrote, that he wrote together with Dectris a few years ago. That's how the Filewriter 1 handles the data. It basically stores the data in HDF5 format, plus it's also used LZ4 and bit shuffle LZ for compression, and takes care of following the standards. But as some of you might know, our detectors have 2 energy discriminating thresholds. And of course, having 2 energy thresholds would increase the complexity of data one has to store. Why would anyone want to use the 2 energy discriminating thresholds? Well, one of the applications can be found by getting rid of the higher harmonics from a sample. So for example, you can see here the same image as on the first slides. It was acquired with Michael Hanfland at ESRF. We used 30 kV X-rays and lanthanum hexabarite sample. The sample has inside the components that produce a higher harmonics energy at 90 kV. These higher harmonics populate the diffraction patterns and create overcrowded diffraction signal where it's hard to take away the signal that we're interested in. So how to deal with that? We suggest applying 2 energy thresholds. Yeah. So the first energy threshold we set to 15 kV to have all the events with the energy above 15 kV, and the second data threshold we set to 68 kV to separate only higher harmonics. Then we subtract the second threshold data from the first threshold data, and we get the diffraction patterns that we are interested in, that are exactly produced by X-rays of a given energy on the sample that we used. But again, our developers have to deal with that and find the ways to handle this complexity. Filewriter 2 is the interface that we currently developed to handle the multi-threshold data and which would be stored in the HDF5 format. And of course, we also want to have following the standard, the Nexus standard, and that's why our developers closely work with NXmx group to solve open questions and resolve bugs. The Filewriter 2 is not yet released, so I cannot give you exact details on how the data is handled, but I can already give a disclaimer that the interface would be able to handle multi-threshold images and would use the virtual data sets to decrease the latency on the input-output. We plan to release the Filewriter 2 interface in August this year. We look for the pilot groups who would like to test that. Then we will plan to accumulate this feedback, implement it, and release Filewriter 2 at the end of this year, beginning of next year. So the future of 2 energy discriminating thresholds is bright. If you want to see more involvement of Dectris in HDF community, I also found few talks from the last year meeting from Herbert Berenstein from ESRF and Diamond Light Source. I recommend you to look into that. And on this, I'd like to thank you for interesting discussions, and I'm looking forward to have more talks and have more questions on how the HDF5 works and how we can handle it how we can use it to handle our data. On that, I thank you from behalf of Dectris, and here's our company with the view on EIGER peak in Engelberg. That's it.
Yes, it works. You mentioned virtual data sets. Does it mean that the different modules will produce different files, and then you will have an HDF5 master file, which will combine these images into one? Or what do you mean by this support for virtual data sets?
Well, I cannot say exactly the technicalities because it's done by our software team. It's not necessarily going to be independent files. The data can be also merged in the interface itself and then produce a merged file. But I can follow up on that.
Question. Thanks, Gigi speaking. So actually, it's the second time today that I saw Nexus mentioned. Actually, is it really, let's say, standard for the format of the file itself? Because if I compare it, for example, to astronomers, they went a different way slightly. There is standardized protocol. So nobody cares how you store your data, but what matters is actually if you offer an interface to access your data, then that is standardized. So is the Nexus actually doing both things, or is it actually just the data format itself?
So the way how we try to describe it within NIAC, which is the Nexus International Advisory Committee, is that there are file formats which specifies each bit in a file depending on its location, what its meaning is supposed to be, and data format, which is basically after modeling your data, defines relationships and what is what. And that's what Nexus does. Nexus describes a whole set of information organized and the relationship between these items and defines what's supposed to be what. And indeed, in Nexus, you can write files in XML. You can write files also with HDF5 as well. And then what you're supposed to have, it's afterwards having a file, which is a Nexus data file, which when you read this, each element supposed to be just assigned to an element of the data model, so you can actually know what is what. And in that sense, I think it's getting similar to the astronomy use case, where you describe what's supposed to be what, and then you can query. Here, there is actually also a tool which writes it into a file as well.